Okay, so hello and welcome back. So in this video I want to talk to you about, I want to tell you a little bit about the concept of LCM and HCF of two numbers. Basically these two concepts are actually very important. I mean, very useful concepts in mathematics. You can use them in many different situations once you understand what they actually are. And to give you a little bit of background as to basically what actually LCM or HCF is. So about the LCM, in very simple mathematics that we learned in class 5 or 6, we said when we wanted to find the for example the sum of two fractions, for example, let's say you wanted to add 3/5 to, or sorry, you wanted to add 3/18 to 3/18 to, for example, I don't know, 5/27. So since you need these two fractions, of course, they don't have a common denominator, and when you don't have a common denominator, you cannot add the two numbers together. So what we did was that we actually somehow managed to get a common denominator by getting the LCM of these two denominators. And of course, instead of doing that, you can simply here write 18 times 27, and then this number, whatever that is divisible by 18 and also divisible by 27. So then you can go in and say, for example, 18 times 27 divided by 18 is equal to 27. So 27, so you have some number 27 times 3, and you have another number 18 times 27 divided by 27, you'll get 18, and that would be 18 times 5. Okay, so that would be basically the sum of these two fractions. But the problem here is that 18 times 27 as a denominator is a fairly large denominator, and you might actually be able to get a smaller denominator for that basically does the job for you as well, meaning that if you multiply 18 by 27, you'll get 56, 5, 16. 16 plus 5 is equal to 21, 0, and then you have a 27 there, so you have 6, 8, and 4, 486. So you see, this is some number like 27 times 3 plus 18 times 5, whatever that is, doesn't matter for now, but the denominator is 486, which is a fairly large denominator. What you could do, what we used to do in order to find the LCM of these two numbers, we usually wrote them as, for example, 18 is the same thing as 2 times 9, and that's 3 times 3. So you can write 18 as 2 times 3 times 3, and 27 is 3 cubed, so it's 3 times 3 times 3. So now the LCM of these two numbers, of 18 and 27 is actually some number that has both of these numbers in it, and basically you don't have unnecessary factors that you don't require in your number, meaning that, for example, the number 486 actually does have the number 18 and the number 27 in it, but it has some unnecessary factors apart from the 18 and 27 as well. So it's and that's basically why it becomes that so much large. I mean, it gets so large as a number. So now what you want to do is that you want to find some number from these two numbers, and you have written out the factors, the prime factors as well. So you want to find some number that has 18 in it and 27 in it, but no unnecessary extra factors in it. So an 18 is a 2 and a 3 and a 3. So it's 2 times 3 times 3. That's an 18. A 27 is 3 factors of 3. So you have 1, 2 factors you already have. If you have another factor over here, you would get 27 times 2, which is equal to, I think, 54. Okay. So now you can imagine that how I mean, compared to 54, 486 is of course a very large number, and you don't need to have this large number over here, because at the end of the day, when you get a fraction, then you want to simplify your fraction to basically to get the simplest form of the fraction that you want. I mean, it's not easy to work with a fraction with a denominator 486 and some numerator, for example, I don't know, 286, 250 or something like that. So you always want to simplify. And when you use the LCM, now this LCM is divisible by 18 and also divisible by 27, and you don't have any extra factors in it. I mean, you have just the factors required for 118 to accommodate 118 and 127, and that's it, right? And if you now use a calculator and divide 54 divided by 18, you see it's a 3, so it's divisible. 54 divided by 27, it's equal to 2, it's divisible. So then you could simply go in here and write this calculation. You can write, for example, 3/18 plus 5/27. You would write this as the LCM. We found it to be 54, and then 54 divided by 18 is equal to 3, so that's 3 times 3 is equal to 9, plus 54 divided by 27 was equal to 2, 2 times 5 is equal to 10, so that's 19/54. And now if you actually do this calculation, this would be 27 times 3 plus 18 times, it would be a very large number, but this is a simple fraction that you can work with. So that's the concept of LCM. And we actually already talked about most of the concept already, but there are a few more things that you want to know about the LCM or the HCF, for example. Let's say that you have let's say that you have a bunch of people. For example, let's say that you have 36 people over here, a group of basically a group A, which consists of 36 people. Okay, so you have 36 people over here, and you have I don't know, you have another group of people over here that is, for example, 356, for example, and 356 people over here. So these are two groups of people, and they want to take part in a march. They want to march, but they want to march in such a way, and they want to march together, but they want to do it in such a way that, of course, when you're marching, you have a certain number of you have basically these rows and these columns. Okay, so you have these rows and these columns, and you have the same thing over and over again. So you have, for example, 1, 2, 3, 4, 5, 6, 7 people in a row, and then you have 1, 2, 3, 4, 5, 6, 7 people, 7 columns, 7 people standing standing in different columns, and that becomes, for example, I don't know what do you call it. This is a group of people marching together, but it has to be, it will, I mean, eventually it will be a rectangle, some rows and some columns. So now we want to know basically what sort of, I mean, if you were free to choose any columns, any number of columns at all, what would be the number of columns that you would choose so that these people could actually march together, and in such a way that these people could actually march together, meaning that these people would have to rearrange themselves in, for example, X number of columns, and then these people would rearrange themselves in the same number of columns, and then this, you would have some sort of configuration like this, and then all of them would be basically practically joined together to make up one, I don't know, call it one marching band, and then the whole marching band is marching together. So now in order to solve that problem, you want to find basically what you want to do here. Actually, what you want to do here, you want to find let me do it first, and then we will get to the nitty and gritty of what that actually is. So you want to find a number, you want to find some number that basically divides 356 and also divides 36, meaning that this number is actually divisible. Let's say that you want to find some number x, and this number 36 is divisible by x, and this number 356 is also divisible by x. And then once you divide 36 by x, then you would have that number of columns, and then once you divide that 356 by that number for this basically no, I'm sorry. Let's actually go and find the HCF of these two numbers, because right now I cannot actually, I'm not finding the right words in order to explain this properly. So let's first go and do the HCF of these two numbers, and then I'll tell you how that concept is actually useful here. Okay, so now let's say that let's first analyze this number 36. Let's see what that is. So 36 is actually equal to 2 times 18, and that's 2 times 9, and that's 3 times 3. So you can write 36 as 2 raised to the power 2 times 3 raised to the power 2. That's basically 36. And 356, you can write it as 2 times 150, 175 plus 178. And don't want to be making mistakes here, so insert 2 times 178 is equal to 356, and then this is equal to 2 times is 50, that's 25, and that's 30, I'm sorry, that's 50, 100 divided by 2 is 50, 70 divided by 2 is 35, and that's a 4, so that's 89. And 89 is divisible, I suppose, by nothing. Probably by, I don't know, 7? No, probably, I don't know. Let's see. What was the number? 89. So if you have 89 over here, you can go to analyzemath.com and use this calculator. Okay, so there is, if you go to analyzemath.com, and there are probably a bunch of calculators here, and then you can use this calculator in order to see whether a number is divisible by 2 or 3, and so on and so forth. Okay, so the number was 89, and you see it's not divisible by 2, not by 3, not by 4, not by 5, and so on and so forth. There is no all the way up to 13. Now, it might be a prime number, so you could go over here, and there is a primes.utm.edu. I found this website somewhere on the internet. You can use it to check whether a number is prime or not. So 89, if you check it, it says 89 is a proven prime. That means that it's actually a prime number. So then you cannot go any further from here. So that means that 356 is equal to 2 raised to the power 2 times 89. Okay. Now, if you want to know how many basically columns of people you can actually rearrange using these basically 36 people and 356 people. If you take the HCF of these two numbers, 36 and 356, what you will get is that the highest common factor, so the common factors between these two numbers, basically you have a factor of 89 here, a factor of 3 here. They're not common, but you have two factors of 2 here and two factors of 2 here. So then I can take two factors of 2. That means that I can take 2 raised to the power 2 out from these two numbers, and that would be, which is equal to 4. That's the HCF of these two numbers. That's the highest common factor of these two numbers. That means that both of these numbers are divisible by 4. 36 divided, and of course I picked these two numbers randomly. I didn't really know whether they would be divisible, what they would be divisible by. But you know that 36 divided by 4 is equal to 9, and 356 divided by 4 is equal to 89. Okay, so, and that's the highest number. That is the highest number. This number over here is actually the largest number upon which both of these numbers are divisible. These two numbers are also, you could argue that both of these numbers are also divisible by 2, meaning that 36 divided by 2 is going to give you 18, and 356 divided by 2 is going to give you 128. But this is the largest number on which both of these numbers are divisible. So then what that means is that this number is going to give you the largest number of columns that you would get in a parade or in a march or whatever you want to call it, if you had 36 people and if you had 356 people, meaning that you would basically divide the 36 people, divide them by 4. So then your 36 would be equal to 4 times 9, which is equal to 36, and 356 you would write it as 4 times 89. That means that here you would get 4 columns, and here again you would get the same number of columns, 4, right? And then of course then you would have basically 4 columns, 4 columns, 4 columns, and so on and so forth, and that would be a, I don't know, marching band or whatever you want to call it. But then you would have the same number of columns all across the whole people. And then out of these people, you would get 9 rows. And out of these people, you would get 89 rows. And that's basically how you could solve this problem. So this concept of HCF is actually can be used in, for example, in a context like this, and it's actually the largest number upon which both of these numbers are divisible. Okay, so now that you have understood at least what you can do with LCM and HCF, let's go and take a couple of examples. Let's find the HCF and LCM of a couple of typical numbers, and then there are also a few things that I can tell you about HCF and LCM, and then we can wrap it up. So, but before I do that, I need to go take a few minutes rest. I'll see you in just a few moments. Okay, so now I was actually watching some video on YouTube. Okay, so now now let's go and find the LCM of a couple of numbers and HCF of a couple of numbers. And once we know that well, then we can have another technique. Okay, so let's do one thing at a time. So what I want to do now is find the LCM of a couple of numbers. Number 2, find the HCF of a couple of numbers, and then there is something which is basically A times B is equal to LCM of A and B, and times the HCF of A and B. And then there is also 2 more things that we can talk about, and then we will wrap this up. Okay, so for example, to find the LCM of let's say you want to find the LCM of so let's say that you want to find the LCM of 6 and 20, right? So, for example, if you have 2 numbers 6 and 20, and you want to find the LCM of these 2 numbers, so what you will do is that you know that 6 is equal, first you always need to prime factorize your numbers, and there is also something called the Euclid's Euclid's division algorithm. Euclid's division algorithm, or Euclid's division lemma. That we can also talk about. Okay, so now if you have these 2 numbers 6 and 20, if you want to find the LCM of, for example, these 2 numbers, is that you want to analyze your numbers, you find the prime numbers of these 2 numbers, and that's always done with the factorization tree, meaning that, for example, 6 is equal to 2 times 3. That's called the factorization tree, as you most probably know. So this is 2 times 3, and 20 is equal to 4 times 5, so that's 2 times 2 times 5, and that would be 20 times 2 times 10, and that's 2 times 5, so that's 2 times 2 times 5. So now to find the LCM of these two numbers 6 and 20, what you will do is that you want to find some number that has both of these numbers in it but no extra factors. So you have for a 6, what you need is a factor of 2 and a factor of 3, so that's a 6. And for a 20, you need a factor of 2 factors of 2 and a factor of 5. So I already have a factor of 2. So then for a 20, I would need another factor of 2 and a factor of 5. And that's basically the LCM of these two numbers. If you multiply these together, that would be 4 times 20, 20 times 3 is equal to 60. And now, as you can see, this number is actually greater than any of these two numbers. This number over here, 60, is greater than any of these two numbers. And it's also divisible by both of these numbers. Okay? So, so that is one thing. And then if you want to find the HCF of these two numbers, 6 and 20, now that you have prime factorized it, now you are looking for the common factors. This is the common multiple of the least common multiple of these two numbers. This is the highest common factor. So you look for the common factor, but for the highest common factor, meaning that between these two numbers, the common factors are basically you have a common factor of 2, and then you have another factor of 3 over here, but there is no commonality between these two numbers as far as the factor 3 is concerned. So you have only one factor of 2. So that's going to be a 2. So now, as you can see, in the case of the HCF, both of these numbers are greater than their HCF, and both of them are actually divisible by this number. 6 is divisible by 2, 20 is divisible by 2. And that's basically how you find the LCM and HCF. And while we are at it, we can actually do, so when you find so if you paid attention to when we found the LCM of these two numbers, we said that we wanted to find a number that contains both of these numbers, meaning that 6 and 20, and for a 6 we needed a factor of 2 and a factor of 3. For a 20 we needed a factor of 2 and another factor of 2 and a factor of 5, and that's basically how we made the LCM. So now what the LCM is, you can formulate this as the greatest powers of the prime factors, as the greatest powers of the prime factors. Okay, what that means, what the greatest powers of prime factors. So for example, here basically the power of the prime factor is basically 2 raised to the power 1 times 3 raised to the power 1, and over here you have 2 raised to the power 2 times 5 raised to the power 1. And the LCM of these two numbers is the greatest powers of the prime factors. So we have the prime factors that we have here are 2 and 3. The prime factors that we have here are 2 and 5. So 2 is basically, you can find 2 in both of these numbers. Now the power of 2 over here is 1. The power of 2 here is 2. And the greatest power of this prime factor is 2. So then you can write 2 raised to the power 2 here. That's the greatest power of this prime factor here. And the prime factor 3 is actually 3 raised to the power 1 over here, and we don't have it anywhere else, so the greatest power of this prime factor is 1. So you write it as 3 raised to the power 1. and 5 is basically the same goes for 5. The greatest power of this prime factor is 1, so times 5 raised to the power 1, which is the same thing as 4 times 3 times 5, which is equal to 60. And that's basically the number that you got here. So that's basically one good way to actually state basically what we did over here formally. And that is basically, and what that means is that the LCM of these two numbers is the greatest powers of the prime factors that you can find in those two or more numbers. And and the HCF is the, you can basically state that formally as the smallest powers of the common factors. Smallest powers of the common factors. Okay, so what that means is that you have these two numbers over here, so the common factors over here are only 2, and the smallest powers of the common factors, here you have 2 raised to the power 1, and here you have 2 raised to the power 2. 2 raised to the power 1, 2 raised to the power 2, and 3 and 5 are not common. So now the smallest powers of the smallest power of these two common factors is of course 1. So you write it as 2 raised to the power 1, which is equal to 2. Okay, so that's basically how you find that the HCF in HCF and LCM in a formal way, but you also need to understand that in an informal way, so because most probably you're going to actually forget. I mean, I know I'm going to forget these two definitions even tomorrow. Today I'm doing this video, and then tomorrow I'm going to forget this. But informally, I know what an LCM is, and I know what an HCF is, and I know how to find them. But if you were to, for example, find the LCM or HCF of two very large, for example, numbers, then finding the LCM and HCF would be a very tedious job, because then you would have to go inside both the numbers manually, and then find the common factors or the greatest powers or the smallest powers, and so on and so forth, and there you could actually make some mistakes. But as far as normal ordinary numbers are concerned, if you know the informal way, you can always somehow get the job done. And there is something else called the Euclid's division lemma, and what that is that when you want to find the let me see what that is. Okay, so basically here we have two things that are interrelated and also related to all of the things that we have talked about here, and that's basically two concepts called the Euclid's division lemma and the Euclid's division algorithm, and you basically need to understand both of them. So now let me actually create another layer over here, call it 28. And what that is that basically first we have the Euclid's division lemma, Euclid's division lemma, and I always actually forget all of these names, but I mean, as long as you understand the concepts, then I think you are fine. Euclid's division algorithm. Okay, so what these two are, basically it's the first one, Euclid's division lemma, is basically a statement of the division algorithm that we normally do. For example, when we say that you have, for example, 8 and 3, you have two numbers, and these two numbers, if you divide 8 by 3, you will get 8 divided by 3 is equal to 2 times 3 is equal to 6, and then you have a remainder 2. And we call this, for example, the dividend, and we call this the divisor. Okay, and we call this the quotient, and we call this the remainder in a what do you call it? In a division. And if I call these numbers A and B, what the Euclid's division lemma says is that for two numbers A and B, for two numbers A and B, let me see. Okay, so basically, if I were to state this formally, so in simple language, what it says is that if you have two numbers, for example, if A and B, when you divide A by B, you are always going to get a quotient and some remainder. This remainder is always going to be greater than or equal to 0, and always less than this divisor, and then you have a quotient that is always multiplied by your divisor to get your dividend. That's basically all that is. Meaning that you can write 8 as 2 times 3 plus a 2. So here is your A, for example, here is your B, and formally we call this the dividend, we call this the divisor, and then this becomes the quotient, and this becomes the remainder. That's basically all that the Euclid's division lemma is. And so to state this formally, it says that given positive integers A and B, given positive integers A and B, there exists unique integers Q and R. There exists unique integers Q and R, Q and R, satisfying this equation, satisfying A is equal to B times Q plus R. And in this equation, you know that your R is 0 is less than or equal to your R less than B, meaning that your R is always less than B. And here is your R, basically. This is your R. Your R is always less than B and is always greater than or equal to 0. Okay. So that's basically the simple division algorithm that we have always used, but this is basically stated in a formal way. Now, the division, the Euclid's division lemma that we have always used in order to divide numbers, can be used in order to find the HCF of two numbers. And then we have a relationship between the HCF of two numbers and LCM of two numbers, and that way you can find basically the LCM as well. And in order to show you why this thing is actually useful, let me show you an example first, and then we can get to the Euclid's division algorithm. So for example, let's say that you have two numbers, 4052 and for example 12,576. You have these two numbers over here and you want to find the HCF of these two numbers. So what you normally do in order to find the HCF of these two numbers is that you have to, of course, go in and analyze them. Do the prime factorization of these two numbers. So you write 4052. This is divisible by 2, so that's 2 times 2000, and that's 26. 2026, and then this is 2 times 1013. And I think 1013 is a prime number, if I'm not wrong. 1000, okay. 1013 is a proven prime, okay. So 1013 is a proven prime. Right, so we cannot, that you can only write as 1 times 1013. You cannot go any further with that. And then when you have 12,576, you can write it as 2 times 12,000 is 6,000 divided by 2. 500 is 250. 76 is 38. 38, so you have 8, 2 and 6, 6288, 6288, and then this divided by 2 is going to give you 3,144. 3,144. This divided by 2 is going to give you 1,550 and 22, so which is 2,71572. 2 times 1572, and then 1572 divided by 2 is going to give you 500 and 250 and 36. So that's going to give you 786, and then this divided by 2. You see, that's a tedious job actually to find the HCF of these two numbers. Well, I'm just going to show you why this is actually very useful, and you're going to see in just a moment how this actually works. So 786 is 350 divided by 2, 40 and 3, so this is 393. So 2 times 393, and this is 6 plus 9 is equal to 15, so this is divisible by 3. 393 divided by 3 is going to give you 1 times 3 is 3, 0, 3 times, and so 131. 3 times 131, and 131 is, I think, is a prime number. 131 is a proven prime. Okay, so you have to stop there. So then you can rewrite these numbers as 4052 is the same thing as 2 into 2 into 1013, and 12,576 is the same thing as 2 times 2 times 2 times 2. So it's a 1, 2, 3, 4, 5. So 5 factors of 2 times 1 factor of 3 and a factor of 131. Okay. And then what you need to do here in order to find the HCF of these two numbers, 4052 and 12,576. In order to find the HCF of these two numbers, you need to find the highest common factors of these two numbers. So you can write this as 2 raised to the power 2 times 10 raised to 1013. So the common factors here are basically 2, and then you don't have a 3 here, you don't have a 131 here, so the only common factors are 2 raised to the power 2 and 2 raised to the power 5. And the highest common factor would be 2 raised to the power 2. There would be 2 raised to the power 2, because you could get I mean, if you write out these two numbers this way, so 4052 would be 2 times 1013, and then 12,576 would be 2 times 2 times 2 times 2 times 2 times 3 times 131, and then you would have one common factor here, one common factor here, and then there would be no common factor. So it would be, the HCF would be 2 times 2. 2 times 2, which is equal to 4. So you see how tedious it is if your numbers get a little bit large, how tedious it is to find the HCF of two numbers. So, and this concept of HCF is actually some concept that can be used in many different applications and in many different contexts. So you need to, of course, understand it really well. It's one of the very foundations of numbers and mathematics. So whatever you want to do with numbers, you need to understand the concept of HCF, and you need to, of course, be able to calculate it. Of course, there are calculators around that would do that for you, but before you can actually entrust that job to a calculator or to a machine, you need to be able to understand the process itself. So now I know that the HCF of these two numbers is 4. Now there is something that Euclid has done, and he must have actually been a very smart person, because, I don't know, Euclid lived 2,000 years ago, I think around 2,000 years ago, and back in those days there was even no paper, there was even no pen, no pencil, no nothing, no calculators. So he had done all of this with actually nothing. He must have been actually pretty smart, right? So what he has done, he has used the Euclid's division lemma, which is basically the normal ordinary calculation, division, in order to figure out the HCF of these of two numbers. And how he does it is that you have these two numbers, 4052 and 12,576. Okay? And what you need to do is that you need to take these two numbers. One of them is always, of course, greater than the other number. So you have a number A, and you get this number as B. And A is greater than B here. So that way you take your numbers yourself in the beginning. And then what you do here is that you divide the bigger number by the smaller number. So you start with 12,576 and you divide it by 4,052. And that's equal to 3 times 4,052 is around 150, and 12,100. So 3 times would be 6, 5, 15, 1, and actually 15, 1. So there is no 1 here. 3 times that's 12. So that's a 0, that's a 2, that's a 4 over here, and that's it. So 420. So you have 420 over here as a remainder. So what you can do, you want to find the HCF of these two numbers, 4052 and 12,576. So you take this number as A again and this number as B, and then once you do this division, you can write 12,576 as 3 times 4052, 3 times 4052 plus the remainder, which is 420. Okay, and then now here you have this, this number was A, this number was B, this number I take it as Q, the quotient, and this number I take it as the remainder. And then what you need to do is take your B, which is actually the divisor here, and divide it by the remainder, meaning that you write 4052 divided by 420. Okay, and that would be, for example, 5, 6, 7 times, 8 times, 9 times. So 9 would be 0, 18, 1, 18, 1, sorry, 9 times 2 is equal to 18, 1, and 36, 37. And then if you subtract, you would get 2, and then you have a 3 over here, 9, and a 15. So that's 7, 2, and 272. So let me do this calculation on a calculator. I'm not sure if I did that right. 4052 divided by 420 is 9.6. And 9 times 420, 9 times 420 is 3780, and 4052 minus 3780, 272. Okay, that was right. Okay, so now you can write 4052, which is this number over here. 4052, you can write it as 9 times 420, 9 times 420 plus a remainder of 272. Okay, still the remainder is not 0, so you just have to keep going until your remainder is 0. And as you can see, while you're doing this, you don't have to prime analyze your numbers, and you don't have to do anything. You just do simple division, and then with the division as a result of this process, you will actually get your HCF. So then the next thing that I do, I take this number and divide it by this remainder. So 420 divided by 272, and that's going to be around 2 times would be 400 and 500 something, so 1 times would be 272, and then you will get, what you will get over here is that's a 3, that's a 12, 11, and that's a 10, so 8, 4, and 1. So you can write 420, you can write it as 1 times 272 plus 148, plus 148. Again, since your remainder is not 0, you need to take this number and divide it by this number, 272 divided by 148. So 1 times 148 is 148, and then you have a 6 here, a 12 here, and then you have a 4 here, a 2 here, and a 1. So 272, you can write it as 1 times 148 plus a remainder 124. and still your remainder is not 0. 148 divided by 124, and 1 times 124 is 124, so that's a 24. So 148, you can write it as 1 times 124 plus 24. And again, these two numbers you can take and divide. 124 divided by 24 is equal to 5 times would be 120. 5 times would be 120, and the remainder 4. So 124, you can write it as 5 times 24. 5 times 24 plus a remainder 4, and then 24 and 4, so 24 divided by 4 is equal to 6, remainder 0. So 24 is equal to 6 times 4 plus a remainder 0. Now that your remainder is 0, the divisor, actually what I did over here was I took this 24 and divided by 4, and that gave me a quotient 6 and a remainder 0. So now at this stage where the remainder is 0, this quotient is actually, this divisor is actually the HCF of these two numbers. So I can write HCF of 4052 and 12,576 is actually equal to 4. And that's basically what we got up here as well. Number 4, and that's basically what we got over here as well as a 4. Okay, so that's actually much more straightforward, and you don't have to analyze your numbers, you don't have to prime factorize, you don't have to do anything like that. You just keep doing a bunch of divisions, and then you will get to your HCF. And one more thing that we have here is the relationship between the HCF of a number. I mean, if you have two numbers A and B, and the HCF of those two numbers and the LCM of those two numbers, okay, the relationship between these four is that the product of those two numbers is equal to the product of the HCF of those two numbers and the LCM of those two numbers, LCM of A and B. So that means that if you have the two numbers and if you have the HCF of those two numbers, then you can simply calculate the LCM of those two numbers, which is for example in this case, the two numbers that you had were 4052, 12,576. The HCF was 4. So you can write 4052 times 12,576 is equal to HCF of the two numbers, which is equal to 4, times the LCM of LCM of A and B. And so if you actually solve this equation, you would get LCM of A and B is actually equal to this whole thing, 4052 times 12,576 divided by 4, which would give you something like, I don't know, 4052 times 12,576 divided by 4 is actually this fairly large number. It's actually this fairly large number. Let me do this again. So 4052 times 12,576 and divide that by 4. It's this number over here, 12,739,488. So the LCM of basically these two numbers, call this A for example, call this B. The LCM of A and B is equal to 12,739,488. And imagine that you wanted to calculate this number. Actually, it would take you forever to calculate it. So it's actually brilliant. Okay. So that's basically all that I wanted to talk about. And we are done. So we talked about HCF, LCM, how to calculate them, the fundamental theorem of arithmetic. We didn't talk about that. We talked about the Euclid's division lemma. We talked about the Euclid's division algorithm, and then using the Euclid's division algorithm, we found the HCF of two numbers, and then we also showed that the product of two numbers is equal to the product of the HCF and LCM of those two numbers, and then using that we also found the LCM of those of two numbers, and we also basically used basically HCF and LCM in two different practical situations where you wanted to find the number of columns in that marching band, and also about adding two fractions together. And that's basically it. I actually found these concepts pretty interesting and pretty fundamental in mathematics, that I just wanted to share them with you. Thank you very much, and see you next time.